Hi everyone, this is Armen from BlueFox AI. I was a former student at the University of Waterloo where I was working with these great professors, Mohammad Javad Shafi and Alex Vaughan. Alex and Javad, they are now working with University of Waterloo and Darwin AI, and this research was sponsored by University of Waterloo, BlueFox AI, and also Darwin AI. So now I'm going to present to you our simple model for improving the adversarial robustness of deep neural networks, which is just simply applying fine-tuning to previously trained models or some kind of pre-trained models. So let's get to it. First of all, adversarial examples in computer vision. I'm sure most of you know at least a bit about adversarial examples, and this very famous sample in ImageNet in which a panda, which in its casual form, it's being detected, classified correctly by a deep neural network model, but after addition of some very small magnitude of noise, the model is not able to classify it correctly anymore, and instead, by very high confidence, it's being classified as some other class. Just to have a definition of adversarial examples or perturbations, very small imperceptible perturbations that can fool deep neural networks by a very high confidence when there is no difference. So apart from the intriguing aspect of the adversarial examples, which can be useful in understanding deep neural networks, there is also another side to them which makes them a threat for many models. So adversarial examples are transferable, which means adversarial examples that are generated from one model can be used to fool another model. And this transferability can happen in the physical world as well. So if you consider security sensitive systems such as autonomous driving systems, this can be a nightmare because we want those models to be intact, and we don't want to have any mistakes, no room for errors. And thinking about adversarial attacks, they can be a big disaster here. And you definitely know about this very famous sample, traffic signs, after addition of some kind of noise to them, they can be classified as other like traffic signs. And imagine just if some stop sign were to be classified as some speeding sign, that can be disastrous even. So what's the solution here? Well, as there are many adversarial attacks algorithms, there are also many defensive mechanisms as well. And this paper is all about just suggesting another method. One of the probably most well-known, simplest, and most effective approaches to increase adversarial robustness is adversarial training, in which we simply augment our training data by adding some adversarial samples during our training. So for that, what we will need to have is to have some adversarial algorithm which would create the adversarial examples during the training and then add them to our training data. So thinking in that way, it's very important to have a very effective adversarial algorithm here, right? The effectiveness of this whole training approach depends on how good is the adversary. So the better the adversary is, the harder samples that it creates during the training, the better the defense would be. But there are generally two concerns about adversarial training. One is whether adversarial training done by some model, by some adversarial algorithm is going to be robust against other adversarial algorithms as well. And other than that, the trade-off between the model accuracy and its robustness. So ideally we want the model to be to have very high accuracy and also very good robustness. But research has shown that this trade-off might not always be so easy to achieve. And although there is a lot of work being done on that, and there have been some improvement, but that's not something that can be achieved very easily. Well, a very good adversarial attack is PGD, projected gradient descent. Very strong one. Using PGD during adversarial training kind of solved the first issue that we had, which is being robust against other types of attacks. Since PGD is the universal first order adversary, which means no other attack is going to, like on average, no other attack is going to provide better attacks, better adversarial samples than PGD. PGD is kind of considered as the universal first order adversary. So robustness against PGD kind of provides some kind of certified robustness for that model, and that's very good in that sense, right? But the issue with the trade-off still exists for PGD. And as I said, there has been some work done to alleviate this effect, works that would try to increase the robustness and at the same time keep the model's accuracy high as well. There has been some progress. But we are going to look at this issue, issue of this trade-off from another point of view. And that's overfitting. Well, overfitting issue for PGD adversarial training. This is the training of like a CIFAR-10 classifier, which is like ResNet models, a simple ResNet model. And so as you can see in this chart, we have three different sets of data here. One is for the models accuracy, killing test accuracy, which kind of increases, but toward the end, it's very consistent, maybe a little drop. For PGD training, like the training data accuracy, the PGD adversarial robustness on the training data, that keeps increasing and increasing, and goes up to 90%, and it can even increase after that. But the PGD adversarial robustness on the test data, it kind of increases up to some point. It's going almost the same speed as the PGD adversarial robustness on the training data. But after a while, the improvement stops, and even we see some kind of decrease here. So as you can see, there is a huge gap here, and therefore a huge overfitting happening between the training data and the test data for their robustness against the PGD attack. But why does the overfitting happen? So here's our hypothesis. We think that, let's consider these two, these circles here as some kind of data set. The orange and red samples belong to one class, and the blue and the cyan classes, they belong to other ones. So like here, cyan ones and orange ones, they are kind of like unseen test data, and like red and blue ones are considered like training data. So what a normal model and even like maybe a deep neural network would do is just find some kind of boundary between the two classes which would maximize the loss. And it's working very fine, right? The model is very general. It might not be robust to adversarial attacks. As you can see, some samples are very close to the boundary. They might pass this boundary just by addition of some small noise. But once we are doing adversarial training, let's say these are the exact same data samples, but in adversarial training, what we are doing, not only we are trying to classify the model, but we are also having some boundaries, like which are kind of set by the value of the epsilon, like how big we want this boundary to be. That kind of sets the whole range of like the whole distance from the sample, right? So here we not only want to classify the decrease the training, like the model loss for the samples themselves, but also for the bubbles which are around the sample, right? So here what happens is that the model has to learn some kind of very complex model which can have an optimal loss for this new bubble-like data. So this would work for the training data and would also provide some kind of robustness for the training data as well. But that might not be the case for the test data. As you can see, many of them are not in the right boundary, and they might not even be very robust to like PGD attack. Even the ones that are being classified correctly might not be very robust to PGD attack here. Well, let's continue and see how we can solve this issue. So our solution is very simple. Don't let the model train for long. Here you can see 6 different charts, like we have 3 charts, and in each of them we have like 6 different experiments. They are basically, all of them are kind of the same, just for different sets of data. So what we do here is that we are getting a pre-trained model. Let's say a pre-trained resonant model for CIFAR-10 data, which has probably 94–95% accuracy on CIFAR-10 test data, right? And then we fine-tune it with PGD adversarial training. So we have a pre-trained model which doesn't know anything about adversarial examples, and then we fine-tune it with PGD adversarial training. So in each of these 6 different cases, what happens is that we are having 6 different steps. So the learning rate scheduling here is just some kind of a stepping learning rate scheduler, in which we are going to have 6 steps. And in each step, we are going to reduce the learning rate by a factor of 10, which is just multiplying the learning rate by 0.1. But the only difference between these 6 different experiments is the number of steps in each of those, like between each learning rate scheduling happens between every 2 updates. So like the black one is having the update like every 1 epoch. After every 1 epoch, we are going to update the learning rate. For like the purple one, the update happens every 5 epochs, and so on for the red one, which the learning happens every 100 epochs. So the red one is going to have the longest time in our training, right? It's going to be trained for at least like 600 epochs. And here are the results. So on the training data, as you can see, the performance just keeps increasing and increasing. Like the more training epochs that we have, the better the performance would be. But on our test data, for the case of clean test data, by clean test data, we mean there is no adversarial attack being done during the testing. You can see that increasing the number of steps here doesn't necessarily help with improving the model accuracy. It actually increases up to some point and then decreases. And this pattern is the worst for adversarial robustness on test data. As you can see, some kind of increase and then a huge decrease. And the model which is having the least amount of training, that one is having the best performance here. So we are going to have this idea, not to let the model train for long, as the key part to this research. And based on this, we proposed a slower start and fast decay method. So basically, we are just working with the learning rate scheduling. We are selecting a pre-trained model. So instead of having a model with no training from scratch and training it with PGD adversarial training from scratch, we are taking some kind of pre-trained model, some model, let's say some ResNet model, which is trained on CFR10, has 94-95% accuracy on ResNet, and then using that and fine-tuning it with PGD adversarial training. So that's what we do, and we use this learning rate scheduler, which we call it a slow start and fast decay learning rate scheduling. So the reason for a slow start and starting from a very small learning rate is that since the adversarial training is new for this pre-trained model, we don't want it to have some kind of a very fast forgetting or like some kind of catastrophe forgetting happen. So we start with a slow learning rate. We increase the PGD adversarial training up to just 5 epochs, and then we decrease the learning rate very fast so that the model would converge very fast. So that's like the learning rate scheduling method that we use. And the results show that this is actually very effective. So here would be the benefits of adversarial training, like adversarial fine tuning. So it's very faster. We are only using it for very limited number of epochs. The overall training would be 8 to 10 times faster than usual PGD adversarial training. Since we are applying it to some pre-trained model, we can do it to any model, like any pre-trained model. Models that if we were to train them from scratch with PGD adversarial training, we might not even be able to reproduce them, since they're like a scale of data that have been used for them is just so huge. For example, the models that have been trained with weak and semi-supervised methods. And like it's mitigating the overfitting issue of PGD adversarial training, as like I showed in the charts. Like the difference between the training and the test PGD robustness isn't that much either, right? So the training isn't that high, it's not perfect yet, but at least the difference between training and test, they are not as much as it were before, right? And very important thing here is that because of the results 1 and 2, like faster training and also being able to apply it to pre-trained model, we can apply this method, adversarial fine-tuning, to ImageNet scale datasets, to samples that maybe we couldn't apply PGD adversarial training very easily before. So let's get to the results here. For CFR10, as you can see, there are many good approaches from before. They've also tried to improve the training time. But so we have the natural one. So natural model is actually the model with no adversarial training, no care for adversarial robustness, very high accuracy, but very poor adversarial robustness. And like PGD-AT is the usual PGD-AT, and these 4 other methods, like our competing methods, the methods that have been proposed recently, and they have some good performance as well, right? They are the state of the art before our method. But our AFT method, as you can see, it has really high model accuracy and also very good robustness here, due to the fact that we don't have overfitting in our like trained models. And this AFT 500 case that other than like the usual PGD, like other than the usual CFR10 data, we are also using 500K like unlabeled data for this training as well. Well, yeah, these are like all clear. The sources for all of these are more clear in the paper itself. And for CFR10, we have like a similar pattern happening. As you can see, the training time for us is very good compared to the like our competitors, and also the results are really good. So here we just have 2 samples for our adversarial fine tuning. In one of them for our PGD adversarial training, we're using epsilon 8 out of 255, but for another one, we are using 10 out of 255. So bigger boundaries usually means the model is going to be robust to a bigger range of, like a bigger bubble, right? So a better robustness, but maybe a lower model accuracy. And you can see here, still the AFT is having a better performance on CIFAR 10 as well, CIFAR 100 as well. And finally, like I guess the most important contribution of AFT model on ImageNet and ImageNet scale datasets. So you can take a look at the results here, but as you can see, AFT, just like any other model, if we have some kind of ResNet 50 pre-trained model and apply it, it's going to have really good performance. So, you know, 69.5 is kind of at performing any other model in terms of accuracy. And the 43% robustness for PGD is like in the same range as any other competitor. But the main contribution comes here when we are able to apply adversarial fine tuning on any pre-trained model. So this SWSL ResNet 50 pre-trained model is a model, like if you go to the paper, you can see the actual source for it. But this model is being trained with a billion scale size data set. So reproducing this result with training from scratch it's very hard. So we may not get the same results, or even if we can get the same results, the problem is that training PGD adversarial training on like billion scale data, that's going to just take forever. So what we are doing here is that we are taking this pre-trained model, we are only fine-tuning it on ImageNet data itself, and only for 10 epochs. And the results here show that the kilodata's accuracy is almost, is very close to natural model, and PGD robustness is like the best, is having the best performance here. Yeah, and here are the results for this paper. Thank you very much. I hope you enjoyed this presentation.